Hello, everybody. Welcome again. We are beginning in on chapter 22 in the Statistics Modeling Our World curriculum. This particular chapter is focusing on a two proportion tests and intervals. So we're looking at the difference now between two proportions. So we have thus far talked about a single proportion. We've done a hypothesis test and a confidence interval when looking at a single proportion. However, comparing two different percentages or proportions is much more common than asking questions about a isolated percentage in itself, right? It's also more interesting. Usually, when we're looking at doing some kind of test, we want to see how two groups differ, right? Is one proportion larger than another to the point where we can say it's not random variation, right? So we're looking at, if you think back to our experimental design, are the treatment that we're imposing better than the placebo control that we've put forward? If it is to the point where it could not be random variation creating this difference, then that treatment is an effective treatment. We might want to say whether this year's results are better than last year's results, right? We can take two proportions for like a percent of products sold, and then we can see if there was some increase over the year that's better, that can be explained as an actual difference, not just random variation. We might want to compare two athletes by looking at a sample of their I don't know, like let's say two baseball players, their batting averages, right? We can compare those as a percent of hits that they've gotten, and run a test. Or is this player definitively better than this player? Is it within or is it within the margins of random variation? So comparing two proportions is a very powerful tool that we're going to look at today. However, we do need another ruler, right? Because we're not just looking at a single proportion. Remember, in the last little bit, the last two chapters about tests and intervals, we were looking at a sampling distribution where P was our sample there, and the standard deviation we were using was P hat Q hat over N, or PQ over N. And we created a sampling distribution of that. Well, we can't do that anymore because we're not looking at a single proportion. Suddenly what we're looking at is the difference between two proportions. So we need to create another standard deviation in order to see that. And you have to remember that standard deviations don't add, right? This goes back to our work in the probability section. I believe it was chapter 16 or 17. So standard deviations don't add, but variances do. So the variance of the sum or difference of two independent random quantities is the sum of their individual variances. Or to put that in equation form, we have this right here. Okay, these proportions being observed are independent, so it's okay to add the variances, and we get a formula like that. So our sampling distribution that we're going to create, instead of it being the center at P or P hat, the center is the P minus P, or P1 minus P2. And then our standard deviations for this is this monster of a formula that we put right there, which is very unwieldy. And in all reality, we probably won't use it to actually do the hand calculations because nobody does that, right? We're going to use a piece of technology to do that for us. So this is the standard error that is going into our test statistic. One other thing is that, so our typical hypothesis for the difference is going to be that there is no difference at all, right? Null hypothesis, no difference between the two proportions. Our alternative hypothesis will typically be that there is a difference, either by saying that one is greater than, one is less than, or one does not equal to 0. Now, we're hypothesizing that there is no difference between the two proportions. That means that the standard deviations for each proportion are the same. Since this is the case, what we do is we pool the counts to get one overall proportion. In other words, when we're finding our sample sizes, we're using pooled amounts to do that. However, I don't want to like overcomplicate this, because again, the technology will typically do this portion for us. Okay? So let's kind of just jump straight into looking at, so again, here's the standard error using the pooled proportions instead of the non-pooled proportions that we had before. This standard error formula, which again, large, unwieldy, is what we're going to throw into our two proportion z-test. So there's my null hypothesis that these are the same. Now, you can write it like this, that P1 equals P2. However, it is more common to write P1 minus P2 equals 0, probably than stating that they're the same. We're using the pooled proportions to do this, so my test statistic looks like this right here. The z-score that I need to find is the difference between my samples, minus 0, over this unwieldy, ungodly looking thing right there. And as long as our conditions are met, we can use this z-score to find a p-value and thus determine the conclusion of our hypothesis test. So what are those conditions before we jump into the actual test? They're basically the same as the previous ones, right? We need randomization. The data in each group, and again, notice that this says each group, so that means for both P1 and P2, we need randomization, okay? Should be drawn independently and at random from a homogeneous population or generated by a randomized comparative experiment, right? We need random data or a representative sample, okay? We also need to make sure that the two groups we're comparing must be independent. This is the only one that is different than a one-prop test, right? We need to make sure. Did I just spell different incorrectly? I feel like there's only one F. See, that's the problem, is I don't have a spell check when I write things. That's the problem. Yeah, I'm just a simple statistics teacher, so. Okay, we need these to be independent. That's the only thing that's different. Randomization, sample size, and then independent groups. We need the groups to not affect each other, right? One of the proportions should not be influencing the other. If there is, then that breaks, and this two-prop z-test doesn't work, right? The solutions that we have, or the result of our hypothesis test is not valid. Finally, we need the sample size. Again, each of the groups must be big enough, and it's the same as before. They need to be at least 10 successes and at least 10 failures. Again, we have to do each of the two samples. So each proportion needs to have a big enough sample size. So let's do an example here. A research doctor has discovered a new ointment that she believes will be more effective than the current medication in the treatment of shingles, which is a very painful skin rash. It is not a fun thing to have at all. Okay, 200 patients have volunteered to participate in the initial trials of this ointment. You are the statistician hired as a consultant to help design a completely randomized experiment. So, after running this experiment, a research doctor found that 75 of the 100 patients who used the ointment showed improvement after the first week, while 62 of the 100 patients who used the control ointment showed improvement in the same time period. Is this convincing evidence that the new ointment is more effective? So we have the new ointment being 75 out of 100. We have the old one being 62 out of 100. is that a large enough difference that it cannot be explained with random variation? We need to do a hypothesis test to figure that out. So, same as before. All of the steps that we're doing for a hypothesis test are the same, right? We're going to follow this hammock over here. Hypothesis, assumptions, conditions, mechanics, and conclusion. I redid this so it's got the relevant details here, right? 62 out of the 100 we should put there. So let's do it. What's my hypothesis? We're looking to see if this proportion is larger than this proportion. So my null hypothesis is that I'm going to assume that there is no difference between them. So P of, and I'm going to say P of T, because P of T stands for the proportion of those with the treatment, minus P of C, which is my control, equals 0. I'm assuming there is no difference. Now my alternative is, the question is saying, is this convincing evidence that the new ointment is more effective? In other words, does it treat more people? So we're still going to have P of T minus P of C. And the question is, what sign do we use? And to figure that out, you kind of want to read the context. We're saying that P of T is going to be larger than P of C, which means that that number that gets created here is going to be bigger than 0. Therefore, we're going to use a greater than symbol. Now, I want to point out that there is an alternative set of hypotheses that we could do here. We could do P of C minus P of T. That's not really well defined there. And then do for the null equals 0. And then for the alternative, go P of C minus P of T. But instead of using a greater than, use a less than, because we're saying that the control is a smaller number than 0. Because if this is bigger, then that's going to make this difference a negative number. Either of these hypotheses work. However, we typically stick with what we have here. But like on the AP test, if you did either of these, you would be fine. You would just have to make sure that your mechanics and your conclusion followed from your hypothesis correctly. So there's my hypotheses, assumptions and conditions. Randomization. Let's talk about randomization first. In this question stem, there are volunteers that did the project, but we could probably make the assumption that because we're doing a completely randomized experiment, that people are being randomized to treatments. So it is safe to assume that patients were randomly assigned to treatments. And remember, in a completely randomized experiment, the randomization that's important is randomizing to the treatments. It's okay to take patients who are volunteers. In fact, if you're testing cream that is going to help with shingles, you need people with shingles. You can't randomly grab people from the population because you need to have volunteers who have shingles. So volunteering for the experiment is okay, but they do need to be randomly assigned to the treatments. So randomization is okay. Let's talk about independent groups. Is it safe to assume that one group is not influencing the other group? And again, in this case, we kind of just have to think about the situation, right? Is it safe to assume that in a research experiment that the patient groups did not have an affiliation, so that like maybe one group is separate from the other? Like they're not like swapping creams and stuff like that. Swapping creams sounds like not a very good thing to say in a video, but that's okay. So is it safe to assume that they're independent? In this case, I think it is safe to assume. It is safe to assume that groups do not influence each other. groups do not influence each other. And we kind of have to figure that one out just based on the experiment. Is there an indication that one group would be influenced by the other? And because we had a randomly assigned to treatments, it's probably safe to assume that they're not influencing each other. So the last thing we need to do then is sample size. And if we want to talk about the treatment group had 75 successes and 25 fails. The control group had 62 successes, which means they had 38 fails. Then we would say both treatment and control had more than 10 successes and failures. So the sample size is large enough. Okay, that enough doesn't look good, but okay. So all of my assumptions and conditions are okay. Randomization, independent group, sample size, they're all good. So the last thing that we're going to write here is that conditions have been satisfied to perform A, and we want to name the test, and this test is named a 2-crop Z test. So there's my assumptions and conditions step. Everything is ready to go. We can run a 2-crop Z test. So I'm going to clear this screen. Now, for the AP test, you can write the whole formula out. As long as you name the test, though, you can actually just do the the calculator output that you would be putting in for the test itself. So I'm going to switch over here to this. So this is a TI-84 that we're going to do this on. Whoop, where did it go? It's over here for some reason. Let's, I don't know. I'll just leave it there. I'm just going to leave it there. I don't know why it's doing that, but I'm going to leave it there. Let's turn it on. All of our tests and intervals are under stat tests, and we're looking for a 2-crop Z test. 2-crop Z test. I'm going to run that in there. This is from a different one, so let's put in all of my information here. So the first thing I want to put in, my X1 would be my treatment group. So that's 75 out of 100. And then I'm going to put in my control group information. That's 62 out of 100. We decided that this was a greater than test because we're seeing if the treatment group was bigger, and that's going to create a positive number in the difference. So that's all my information, and you can literally just enter that information as part of on the AP test. They're okay with that. So that's what I got. My Z-score is 1.97 with a p-value of 0.023. So we want to remember those numbers, 1.97 and 0.023. So coming back over here, 1.97, 0.023. 1.97, 0.023. My Z-score was 1.97 and my p-value was 0.023. The other information I want to put down is everything that I put down for on that calculator wizard, which is 62, and that's 100. Okay. So there's my p-value, 0.023. So the last step here is to write my conclusion. And remember, when we write our conclusion, we take a crap, or a craps. Right? Context, reject or fail to reject. The AS is assumed significance, which we were not given an alpha value in this one. So we can we'll create one ourselves. Generally, we use 0.05, and the last one is state your p-value. So let's write a conclusion based on my p-value. Of 0.023, I reject the null hypothesis at the alpha equals 0.05 level. There is evidence to suggest. Remember, we haven't proven anything. There's evidence to suggest. There is evidence to suggest that the treatment performs better than the control at treating shingles. Woo-hoo. And there is a great conclusion for what you might end up having to put on your AP test. Again, the context can be seen in this sentence right there. I like to highlight things. The reject or fail to reject is me stating that right there. The assume significance. Oh, I already used green. What am I doing? What do I want? Light blue. We need to highlight that. The assume. What happened? It was supposed to be blue. Let's try this again. Blue. Light blue. Assume significance is me stating that right there. And then finally, the part where I do my p-value, we'll do in purple, is that right there. Right? So all parts of a good conclusion are there. And that concludes this video. We'll have another one about creating a 2 proportion z interval from this chapter, with maybe a third video with some additional examples being done. However, this would be it here. If you have questions, feel free to leave them in the comments, and I'll do my best to get back at you or try to contact me in some way there. Thank you very much for watching, and we'll see you another time. Bye.